Welcome back to the deep dive. Uh, ever really stop to think about electricity? I mean, beyond just flipping a switch.
It's pretty amazing stuff.
Right. It just works, zipping through walls, powering everything. But, how it actually works often feels a bit mysterious.
Like magic sometimes.
Exactly. Imagine if it wasn't predictable. If turning on a light was, well, a gamble. That's kind of where things were before a really key discovery. So today, we want to go beyond that switch, our mission, unpack the basics. We're talking Ohm's law, how things get connected in circuits.
Yeah, the fundamentals.
And we want to do it in a way that hopefully makes it click. So you can really get a feel for how things are powered day to day, not just memorizing stuff.
Absolutely. And look, for this deep dive, we're drawing from a great source, Young Track.
Yeah, which translates to.
Something like True Beginner's First Steps in Electricity. It's perfect because it's really designed for that foundational step-by-step understanding, making it accessible.
Okay, perfect. So we'll start with that core relationship voltage, current, resistance, the real ABCs. And then we'll move into how components, lights, motors, whatever, actually get wired up in the real world.
Sounds like a plan.
All right, let's dive in. Voltage, current, resistance. We hear these words all the time.
Constantly.
Even if you kind of know what they are, getting how they, dance together is key. Before the math, what are they, physically?
That's the best place to start, definitely. Think of it like water in pipes. That's the classic analogy, and it works pretty well.
Okay, I can picture that.
So voltage V, that's like the water pressure, the push, the force making the electrons want to move, higher voltage, more push.
Right, more pressure.
Then current, that's the flow rate. How much water or how many electrons are actually moving past a certain point per second.
Okay, the amount flowing.
And resistance R, that's like how narrow the pipe is, or maybe some gunk in the pipe. Anything that makes it harder for the water or the electrons to flow, it resists the movement.
Okay, so pressure, flow, and something slowing it down.
Exactly. And the really cool part is how they're all tied together. You can't change one without affecting the others. Our source gives a really simple way to see this. Having just one wire, okay?
Yeah.
If you apply, say, 10 volts of that electrical pressure across the ends of the wire,
Okay, 10 volts of push.
then you measure 1 ampere of current flowing through it.
So 1 amp of flow rate.
Then that wire, just by definition, has a resistance of 10 ohms. That specific relationship voltage, current, resistance, that's what Ohm's law nails down with math.
And it's named after Georg Simon Ohm, right? A German physicist.
That's the one,
Okay.
from 1789 to 1854. And yeah, his big contribution was mathematically connecting these three things.
Was it like an instant hit? Or did people push back?
Yeah.
A bit of resistance to the idea.
Huh, nice one. Yeah, there was a bit of skepticism at first, actually. Science can be like that. But his core idea was just so elegant, so powerful. Basically, he showed that current equals voltage divided by resistance, the famous I equals VR. And this wasn't just, some neat equation. It basically launched electrical engineering as we know it.
How so?
Well, think about it. Before, building something electrical was kind of guesswork, like building a bridge without knowing physics. Lots of trial, lots of error.
Right. Maybe it works, maybe it catches fire.
Exactly. His law gave people a tool to predict how electricity would behave, how much power you need, how thick a wire should be. It made everything safer, more reliable. Phones, computers, the power grid, it all leans on this.
Wow. So fundamental.
So fundamental, they named the unit of resistance after him, the ohm, that little mega symbol.
Okay, but formulas.
Hmm.
They can sometimes make people's eyes glaze over.
Totally understand that.
Does the source give us a way to, visualize this without getting tangled in the algebra?
It does, and it's really clever. It's called the Ohm's law triangle. Super helpful mnemonic.
A triangle. Okay, how does that work?
Just picture a triangle. At the very top, the peak, you put V for voltage.
U at the top. Got it.
Then, on the bottom level, side by side, you put I for current and R for resistance.
Okay, V on top, I and R below.
Now, here's the magic. If you want to find one of these values, just cover it up with your finger. The triangle shows you the formula.
Oh, neat. Okay, show me.
So, cover up V at the top. What's left?
I and R next to each other.
Right. So, voltage equals current times resistance. V on top, R underneath it, like a fraction.
Now cover up I. What do you see?
V on top, R underneath it, like a fraction.
Exactly. So current equals voltage divided by resistance. I equals VR, the original formula.
I, V over R.
Got it.
And last one, cover up R.
V over I.
Perfect. Resistance equals voltage divided by current. R equals VI. See? One little triangle, all three formulas.
That actually is really helpful. Much easier to remember than just three separate equations.
It really is. Makes it much more intuitive.
Okay, let's try it out. The source gives some examples, right? To make sure we've got it.
Yep, let's run through them.
All right, first one. Circuit has a resistance of 10 ohms, and there's 5 amperes of current flowing. What's the voltage?
Okay, use the triangle. We need voltage, V, cover V.
I times R. So 5 amps times 10 ohms.
Which gives you?
50 volts.
Exactly, 50 volts.
Okay, easy enough. Next scenario. We know the voltage is 50 volts, and it's applied across that same 10 ohm resistance. What's a current?
All right, this time we need current I, cover R.
V over R. So 50 volts divided by 10 ohms.
Yep.
That's 5 amperes.
Perfect. 5 amps. It all lines up.
Last one, 50 volts applied, and we measure 5 amperes flowing. What's the resistance?
Need resistance R, cover R.
V over I. So 50 volts divided by 5 amperes,
Gets you.
10 ohms.
Bingo. See how consistent it is? No matter which piece you're missing, the law holds up.
That's actually pretty cool. It's like a perfect little system.
It is, and that predictability, that robustness, that's why it's so crucial. It's the bedrock. Understanding this is really the first major step to getting how all our electrical stuff works.
Okay, so we've got the basic relationship. V, I, R. Pressure, flow, resistance, all connected by Ohm's law.
Nailed it.
Now let's think about putting things together. Like, how do you actually hook up those lamps or resistors or whatever to the battery or the power source?
Right. Because just having the parts isn't enough. How they're arranged matters a lot.
The source mentions 2 main ways, right? Series and parallel.
That's correct. Series and parallel are the 2 fundamental ways to connect components in a circuit. Let's tackle series first.
Okay, series connection. What does that look like?
Imagine you have a battery and, say, 2 lamps. In series, you connect them end to end, like links in a chain.
Okay, one after the other.
Exactly. So the electricity flows out of the battery through the first lamp, then immediately through the second lamp, and then back to the battery. There's only one path for the current to take.
Like a single-lane road. Everything has to follow the same route.
Perfect analogy. And because there's only one path, the amount of flow is the same everywhere in that circuit. The same current goes through the first lamp and the second lamp.
Okay, constant current. What about resistance in series?
It's simple addition. The total resistance of the whole circuit is just the resistance of the first lamp plus the resistance of the second lamp, and so on for however many things you have in series.
So more things in series means more total resistance.
Definitely. And think back to Ohm's law. I equals VR. If the voltage from the battery stays the same, but the total resistance goes up.
Then the current I has to go down.
Precisely. So if you connect lamps in series, adding more lamps increases the total resistance, which reduces the current, and that means they get dimmer.
Okay. That makes sense. More resistance, less flow, less light.
You got it. Now, connecting batteries in series is different. That adds voltage. But for things that use power, like lamps or resistors, series adds resistance.
So is series common? It sounds like it might have downsides.
It's simple to wire, but yeah, there's a big one. Think about that single path again. What happens if one lamp burns out?
Uh-oh. The path is broken, like a drawbridge being up.
Exactly. The entire circuit stops working. If one component fails in a series circuit, everything goes dark.
I feel like I've experienced that with old holiday lights.
You probably have. That's a classic example. One bad bulb, the whole string dies. Frustrating.
Right. Very. So that single point of failure is a big drawback. What's the other way then? The parallel connection.
Right, parallel connection. This is different. Instead of end-to-end, components are connected side by side.
Side by side, how does that work?
Imagine the wires from the battery splitting. One wire goes to the first lamp, and a separate wire goes to the second lamp. Then on the other side, the wires from both lamps come back together before returning to the battery.
So it creates multiple paths, like the road splitting into multiple lanes.
Exactly, like a multi-lane highway. The current flows out of the battery, hits that split, and some goes through lamp 1, some goes through lamp 2 simultaneously. Then the currents rejoin on the other side.
Okay, so the current splits. What about voltage in parallel?
This is the key difference. In a parallel circuit, each lane or branch gets the full voltage from the source. Both lamps see the same battery voltage.
Oh, so even though the current divides, the voltage is the same for both.
Precisely. And because each lamp gets the full voltage, unlike in series where the voltage gets divided among the components, lamps in parallel will shine much brighter, assuming they're the same lamps and battery.
Brighter and?
Yeah.
What about that failure problem? If one lamp burns out in parallel?
Ah, see, that's the beauty. If one lamp's filament breaks, it just means that one path is broken. The other lamp still has its own complete path back to the battery.
So the other one stays lit.
Exactly. The rest of the circuit keeps working. Much more robust.
That sounds way more practical for most things.
It absolutely is. Think about your house. All your outlets, your lights, they're wired in parallel.
Ah, that's why plugging in a toaster doesn't make the lights dim usually.
Right, and it's why if one light bulb burns out, the rest of the lights in the room stay on. Each appliance, each light, gets the full household voltage, maybe 120V or 220V, depending on where you are independently.
Okay, that makes total sense now. Series adds resistance, divides voltage, has that single point of failure. Parallel keeps the voltage the same across components,
Oh,
allows independent operation.
you've summarized it perfectly. Those are the core differences.
Wow. Okay, we've really covered some ground.
Mm-hmm.
From Ohm's law, that VIR triangle,
Mm-hmm.
all the way to how putting things in series versus parallel completely changes how a circuit behaves. It's clearer now. You really start to see the logic behind it all.
Good. Because it's not magic, right? There are rules. And once you understand them, even just the basics, like Ohm's law and series parallel.
It demystifies so much.
Exactly. And knowing this stuff isn't just for engineers. It's useful for anyone who uses electricity, which is, well, everyone. Whether you're just curious or maybe thinking about a little DIY project, understanding the fundamentals is key.
So for you listening, what does this really mean? It means you're not flying blind anymore when you think about how that light switch works, or like we said, why some holiday lights are such a pain.
Right. You have the basic concepts now.
You got the vocabulary, the framework, it's a foundation.
Definitely. And it leads to some interesting practical thoughts. Here's something for you to chew on, based on what we discussed.
Okay.
Think about those little decorative string lights again. We know what happens if one bulb burns out in series versus parallel.
Right. Series goes dark, parallel keeps going.
So, considering that, which type of connection series or parallel do you think is mostly used in those cheap strings of holiday lights you buy? And why might they choose that method, even with the potential downside?
That's a good question. Cost versus convenience, maybe?
Maybe. Something to observe and think about next time you see them.
Definitely food for thought. Apply these ideas, look around you, and you'll start seeing these principles everywhere. Hope you enjoyed this deep dive.
Yeah, I hope it was helpful.
We look forward to the next one.